Hello and welcome back to the Networking Fundamentals section of this course. In this video, we'll be discussing IPv4 addressing and binary conversion. Now, fundamentally, even though our IP addresses are written in dotted decimal format, where we have 4 sets of decimal numbers ranging from 0 to 255, and we have 4 sets of these. So we could have 192.168.1.1, and this is a valid IPv4 address. Fundamentally, what's happening is these decimals are just written in a manner that's easier for humans to understand. These are actually each 8 bits long, which is 1 byte. So to understand how subnet masks and IP addressing really works, we really need to understand what's happening at the binary level. So with that, it'll be much easier if we learn how to count in binary. So as I mentioned, each section of our address is 8 bits, or 1 byte. These are equal to each other. The way we count in binary is that each position from right to left is an increased power of 2, starting with 2 to the power of 0 on the far right, and going to 2 to the power of 7 on the far left. 2 to the 0, it's okay if you haven't done exponents in math for quite some time. 2 to the 0 is the ones place. So in this second row, we have what place each of these are. So the first section is the ones place, 2 to the 1 is the twos place, 2 to the 2 is the fours place, etc., moving up to the 128 place. And what we do is we add together all positions which are a 1 to convert the binary number to decimal. As we see here, we have 10101100, and this comes to be our 128's place plus 0, and our 32's place plus 0, plus our 8's place plus our 4's place plus 0 plus 0, and this gives us an answer of 172. So if our IP address started with 172 in the beginning, so it was 172.16.0.1, then our first octet here would be 10101100, the same as what we have here because it is 172 as the decimal format. So I know this can be a little weird to wrap your head around. Because of that, I've included here some examples that we can run through briefly. Really common numbers that you'll find are the 192.168 address, our Class C addresses. That these are 192 is 11000000, because we add 128 and 64 to get 192. And then 168 is 10101000, because 128 plus 32 is 60, and then our 8's place to get 168. Our 10s, so 10.1.1.1, our first octet there would be 00001010, because we need to add our 8's place and our 2's place to get the number 10 in decimal. Counting in binary is really important for variable length subnetting, and that is included on the exam now. I would make sure that you feel comfortable in counting in binary. You can run through these examples, and there's also a practice test with this section to try and really solidify that information. So now that we have a sense of how to count in binary, let's take a closer look at the format of the IPv4 address. So the IPv4 address is a 32-bit address field. As we mentioned, there are 4 octets, and it's called an octet because each section is 8 bits long, and the entire field is 8 times 4, which is 32 bits. So the IPv4 address, when mixed together with a subnet mask, that it is comprised of a network identifier and a host identifier. The definition of host and network portions is defined by the network mask. So a network mask works by having a series of consecutive ones and then a series of consecutive zeros. All corresponding positions, which are a 1, is the network portion of the address, and all corresponding positions that are a 0 is the host portion of the address. I know that might be a little strange to wrap your head around. Let's take a look at the next slide here, and this might become a little more clear. So down here we have the IP address of 172.16.10.5, and it is a /21. So the 21 in CIDR notation, that's classless interdomain routing notation, and this is often referred to as a prefix length of being a 24 length prefix. The number there, the 21 in this case, is 21 consecutive ones. So we have 8, 16, 17, 18, 19, 20, and 21. So we have 21 ones. Now let's take a look at this. We have right above it the IP address expressed in binary of 172.16.10.5. Now each corresponding position that is a 1 is part of the network portion. So the first 21 bits up to here are part of our network. So that means everything else is part of our host section. In order to determine what the network identifier is, the first address that is in that network, we go ahead and do a logical AND operation, which means both corresponding numbers must be a 1 in order for the resulting number to be a 1. So in this case, we have 1 and 1 in the first place, 1 and 1 in the third, 1 and 1 in the fifth and sixth, and we see we've got 1, 0, 1, 0, 1, 1, 0, 0, and continuing along up until here, our 21st position, where we have the last 1 in our mask, and all other numbers here are going to be zeros. If we add this up in binary and convert it to dotted decimal, we get this address, 172.16.8.0/21. That this is the network identifier, the first address in the network that this IP address is a part of. Okay? Now, we worked with a 21-bit mask here, and up here we have a 24-bit mask, and see that it is on the bit boundary, is what we call it, when it is increments of 8, and on the bit boundary here of being at the dot. That makes it really easy to calculate our network ID, because any area here that's zeros, that whole octet will just be 0 for our network ID. So if I was the address 192.168.10 192.168.16/24. And since this is a 24-bit mask, we see that just the last octet here will be 0. So our network identifier would be 192.168.10.0/24. Right, so that's how we calculate the network ID of our IP address, of our subnet. That our IP address is also paired with our subnet mask to identify what network that address is part of, and then what the host identifier is within that network. Excellent. So let's talk a bit about some different types of IPv4 addresses. So a really famous IP address space is the RFC 1918 address space. This is an address space that is only used for private addressing. This is not routable on the internet. If you tried to advertise these addresses on the internet or tried to, say, ping 192.168.1.1 over the internet, it wouldn't go anywhere, or at least it shouldn't. Some service providers leak these addresses accidentally or purposefully, but regardless, it shouldn't actually go anywhere. It does not uniquely identify any device on the internet. So there are 3 address spaces described in RFC 1918. It is 10.0.0.0/8, 172.168.0.0/12, and 192.168.0.0/16. Now, these spaces can be described in classes. So Class A networks are /8 networks. It doesn't really matter if it's actually in the 10 dot address space. It's just any /8 network is considered a Class A network. Similarly, a Class B network is a /16. So recall that these are 8-bit subnet masks and 16-bit subnet masks. And a Class C network is a 24-bit subnet mask. And below each of our private address spaces here, we see that the 10 space gives us a single Class A network, a single /8 Class A network. The 172.16 space gives us 16 contiguous Class B networks, so 16/16 networks. And the way this would work, right, is we've got 172.16.0.0/16. The next one is 172.17.0.0/16, and moving on up into the full 16 here of being 172.31.0.0/16, etc. Excellent. I appreciate you going through this with me. I hope that this has been informative for you, and I would like to thank you for viewing.